Everyone, let's start off. Great. Let's start with a question. Last thing we did was this one. So we got a stationary wave. Y is equal to 2a sine kx cos omega t. Find the energy of one loop. So if you see this is x is equal to 0, this will be x is equal to lambda by 2. So if you have a wave which is moving, then that means there's also an energy. Find energy of one loop. So here you can actually use those formulas we derived before. The potential energy of a segment half tension dou x by dou x whole square. Kinetic energy is half mu dx dou y by dou t whole square. And you have to be careful here in this scenario. The potential energy of a segment is not equal to kinetic energy of a segment. This is valid only for a progressive wave. In a stationary wave, this is not equal. And if you remember how we derived this also, remember in a progressive wave, there's a second condition. Dou y by dou t is minus v wave dou y by dou x. Because of that, they became equal. Now they won't be equal because that condition won't be satisfied for stationary wave. So let's see how will we do this. I'll show you this in two different ways. One, there is a much faster way to get this. One will give you a complete analysis. Try, take out 2 minutes, then I'll show you. Let's see. It's more of a math. See, and you will see some interesting stuff, and then we'll try to put this also theoretically. So potential energy, if you take a small segment of TDX dou y by dou x whole square, it's a partial differentiation. So when I differentiate this x, that sine kx may k will come out. And what is tension? V wave is nothing but root over T by mu. So T is equal to mu V square. And we also know V wave is equal to omega by K. So K into V wave is omega. So half tension will be mu into V square. Dx dou y by dou x will be 2ak cos kx cos omega t whole square. That V square k square will become omega square. You end up with half mu square a square omega square. That is there are two there. In dx cos square kx cos square omega t. This is the potential energy of a segment dx at x coordinate with time t. Kinetic energy of the dx is half mu dx dou y by dou t whole square. This also comes out to be 2 mu a square omega square dx sine square kx sine square omega t. Now, when you add them, total energy, and you can clearly see both are not equal. The total energy dx will be two mu a square omega square dx cos square kx cos square omega t sine square kx sine square omega t. And you can clearly see this is not constant. That means in a stationary wave, if you take a small segment, energy is not constant. But the thing is, whenever you open any book, you will read this thing. Total energy of a loop is constant, which is true. But problem is, because people keep remembering that word total is constant. When they ask for segment, they think it is constant. So the total loop energy will be constant. We will prove that. But for a segment, it won't be constant. How do you find the total energy for a loop? So total energy for a loop, integral dE dx 0 to lambda by 2. So basically, you're integrating with respect to x. So time is constant. 2 mu a square omega square cos square omega t integral 0 to lambda by 2 cos square kx dx. And we know sine and cos function average value for one time period will be half. So this comes out to be lambda by 2 and this comes out to be lambda by 2. You can check it out. And when you add this, you get the total energy of a loop. 2 mu a square omega square lambda by 2. You get cos square omega t plus sine square omega t. So this cos square ka term is your potential energy ka term. This will give you the kinetic energy of the loop. Yeah, you have to multiply that thing though. That's not lambda by 2 actually, it's lambda by 4, sorry. Because you'll get 1 minus cos 2 omega 2 by 2, na? Now if you see, this comes out to be constant. That is half mu a square omega square lambda. The total energy of a loop is constant, but each segment is changing. There, we just used max and just brute force, like we just kept it there and we just kept solving and we got the answer. But there's more intuitive way of doing this without doing this much math. This thing has its own advantages. You can clearly see how the energy is changing for each segment. And you can clearly see the potential and kinetic are not equal for a segment. Like a progressive wave, they used to be equal. Here it is not. So what is the other intuitive way of doing it? Think about it. What is a stationary wave? A stationary wave is nothing but a combination of two waves. So that means when I take one loop, can I say like this? You're pushing two waves from left and right. So end of the day, power is entering from both the sides, which is half mu a square omega square v wave. From here also the power is entering half mu a square omega square v wave. And this distance is lambda by 2. So forget about the waves. If I just ask you like this, for how much time does this power entering this region? For dx total energy would be constant. But there are external forces here, right? Particles are executing SHM, right? But here there are external forces also. There are tensions on both the sides. The energy is actually continuously moving in and out. So power is entering inside. So for how much time is the power entering inside? So the time for each wave to cross the loop will be lambda by 2 v wave. So that means the total energy inside the loop. Think of like this. Let's say 100 joules per second is entering from both the sides. And it takes 5 seconds for the wave to cross this loop. That means for what? For 5 seconds, you're pumping energy inside 100 per second, isn't it? So you're pushing 500 joules from left and 500 joules from right. And where is all this energy? Shouldn't all that energy be stuck inside that loop? The total energy of the loop will be 2 times power into time. There, you get the same answer. Much faster, no integration, nothing. Actually, if you remember, the power ka formula also we derived from integration only. So we are actually using that result directly now. Is this making sense, everyone? So if they ask you this in the exam, I would say this is a better way to remember. So a loop is nothing but two waves entering from left and right. So if you look at the node now, energy entering the node is equal to energy leaving the node. So the total energy is constant. Total energy is not crossing the node. But whatever energy has entered inside stayed inside for some time. Is that making sense? It's like this, you have a room. Let's say people are walking into the room. So every second, two people are entering the room and it takes them 10 seconds to cross the room. Means what? At any point of time, there are 20 people inside the room, isn't it? If every second, two people are entering. And if it takes 10 seconds to cross, that means for 10 seconds, people are going in, but no one is coming out. And the 11th second, two people will come out and two people will enter. Now you reach a steady state. People entering is equal to people leaving. But at any point of time, 20 people are stuck in the room. Is that making sense? Now, if you try to see this a little theoretically, you'll notice a lot of things. So when the loop is at the extreme position, look at the segmented antinode. You'll observe if you take a small segment dx at the antinode, the length will be always same. Check it out. At any point of time, the slope is always 0. That means the antinode never gets stretched. So potential energy of dx is 0. Kinetic energy of dx is also 0 because it's at the extreme position. Now, when it comes to the mean position, it is in natural length. So potential energy is 0. Kinetic energy is maximum. Check it out. If you remember in progressive wave, both are maximum, both are minimum. Here, if you see the segment at an antinode will never stretch. It will always remain flat. So there's no potential inside it. Again, elastic potential energy. So you will observe there is no elongation in a segment dx at antinode. Similarly, if you look at the segment at the node, again, you will see something similar there. Here, the node ka point will never move. The kinetic energy dx will be 0. Potential energy of the segment is 0 because it is a natural length. And when it stretches to the extreme, you can see this part has stretched a lot. Potential energy becomes maximum. The kinetic energy is still 0 because a segment near the node will never move. You can clearly see here the total energy of a segment is not constant. The problem, right? Everywhere we keep studying about the loops only. We don't exactly talk about how is the energy, what is happening inside. And this will create problem. When they ask more than one choice questions, you will get questions of this sort. So what is exactly happening? So if you look at this loop here, you'll notice something. When the string is extreme, maximum stretched, observe this. At the antinode, your potential was 0. Kinetic was 0. At nodes, the potential energy was max. Kinetic was 0. And when the same string becomes flat, at the antinodes, potential was 0. Kinetic was max. Potential is 0. Kinetic is 0. That means when the string is moving from extreme to mean, look at the antinode. Antinodic energy was 0. But when the string becomes flat, suddenly it gained energy. That means energy is transferring from nodes to antinodes. Similarly, when the string is going from mean to extreme, look at this thing. Nodes have 0 energy. Suddenly they'll gain energy. That means the energy is going back again from antinodes to nodes. So energy of a loop is constant, but within the loop, the energy is being continuously redistributed. This will be a good theoretical question. In a stationary wave, when the string is going from extreme to mean, how is the energy transferring? It's going from nodes to antinodes or antinodes to nodes. Now, if you have no idea, you will feel like, what the hell? Matlab, what is energy? So is constant. So if I put this in statements here, and string goes from extreme to mean, nodes to antinodes. And if you notice something more, this energy actually goes to antinodes and again comes back. It will never cross the antinode. Did you observe? It will never go to the other side of the antinode. That means the energy is actually redistributing only in within half of the loop. The energy does not cross the antinode because energy is coming from both the sides, symmetry, right? So energy stops at the antinode and again goes back from there. And similarly, energy never crosses the nodes also because the nodes are fixed. If you see, energy doesn't get out of the loop. And within the loop, energy is always being redistributed. Energy is being redistributed. But the total is constant. It's like you're shifting your money from left pocket to right pocket and right pocket to left pocket. But the total money you have is still constant. Because the total power entering from left and right are equal, Aditya. So at a node, there are two waves, right? So if both the waves are going equally, same power is entering and leaving. So total has to be constant. So we're talking about net transfer. If you ask me, energy is not flowing. Yeah, it is flowing, but whatever is coming from right, same is going left. So you can't tell the difference. Clear with this? Yeah, that's a bit of a discussion about the energy thing there now. But if you take the whole loop, now if you see the whole loop, the string is maximum stretched. So potential energy of the loop is maximum. This is where you will see this thing everywhere. So be careful. Segment, loop are completely two different things. So kinetic energy of the loop is zero. When you come to the mean position, potential energy of the loop is zero. Kinetic energy of the loop is maximum. So total energy of a loop is constant. And you actually use this thing. But the thing is, you didn't realize at that point of time because you didn't have an idea. Anyone remembers what is Rutherford ka drawback? In atomic structure, when you studied Rutherford model, anyone remembers what is one of the major drawback? According to classical theory of electromagnetism, an accelerating charged particle emits photons. An electron going in a circle has centripetal acceleration, so it should continuously emit photons and therefore lose energy and eventually collapse. Right, Ansh. And then Bohr's comment says there are some specific orbits, right? Electrons will go in circles, but as long as they go in these specific orbits, they don't lose energy. The energies of the orbits are constant. These orbits are called stationary orbitals. Did you hear the word stationary orbitals? Maybe it didn't ring a bell then. So if you go to this Bohr's theory, so if you look at the second postulate, angular momentum is quantized, where mvr is equal to nh by 2 pi. This can be written as 2 pi r is equal to nh by mv, and we know h by mv is nothing but lambda de Broglie wavelength. So what this thing saying is the circumference 2 pi r is an integral multiple of lambda. Basically, it forms a stationary wave. And this n is equal to 1, 2, 3, 4 principal quantum numbers are actually harmonics. So as long as the electron goes in this particular orbits, the wavelength is an integral, circumference is an integral multiple of lambda. It forms a stationary wave, and therefore the energy remains constant. How did you think we got this angular momentum as quantized? So you can actually get it from the stationary waves also. You can get it experimentally also. So this is again another way of asking. This is how you can combine waves with this Bohr's theory. They do such stuff, huh? You get hypothetical questions like this. So this is the idea there. So whenever you say the energy of an orbit is constant, it forms a stationary wave. That's what remains constant. If you go to any other orbit, you don't form a stationary wave. So electrons can't remain in that orbit. Orbits form a stationary wave. And the principal quantum number, if you see, is actually harmonics. Or else why it should be an integer. Therefore, energy of an electron in an orbit is constant. Again, you'll notice these kind of questions in modern physics. The next one, after wave optics. There. So just have an idea like this, because you will find advanced paragraphs something like this, and you will get scared like, oh, what the hell they're talking about. So you have seen this in chemistry, but at that point of time, you really didn't have an idea. Now you have enough knowledge to understand why it is called stationary orbit and all that nonsense. Clear with this? And others do keep your cams on. There, that's a little bit of an energy, right? We proved both the ways mathematically and also with pictures. Next thing, any doubts so far? So all the discussion we did about the segment, energy of a segment is important. You will mostly get those things in forms of, more than one choice questions. And that discussion is one of the most, very less discussed. You'll find it in very few places, but you will find, but it's not really that discussed in detail. That's one important stuff. Next thing, the general equation of a stationary wave. So if you actually look at your general equation, which we showed till now, y is equal to 2a sine kx cos omega t, that's actually a very special case. The general equation looks like this. Y is equal to 2a sine kx plus phi 1 sine omega t plus phi 2. You get actually two phasors. So the first phi 1 tells you the position of origin. I'll give you some examples. This tells us the position of string. At t is equal to 0. So let's take our the common thing which we are using. So whenever you're writing y is equal to 2a sine kx cos omega t, what do you mean by that? Again, understand, the stationary wave doesn't care who is looking at it. Let's say we have a stationary wave oscillating in a lab. I enter the room. I see this at some position. You see this at different position. Do you think we both write the same equation? I have to show some difference in the equation, right, to represent that we're seeing at different times. Now look at this equation here. The amplitude is 2a sine kx. That means when you put x is equal to 0, there is a node. So if you substitute x is equal to 0, you will get amplitude 0, and that is a node. That means whenever you write this equation, you are taking the node at an origin. Second thing, when you put t is equal to 0, you'll observe the function is maximum. Cos omega t, that means all the points are at their respective maximums. That means for this equation, the string actually looks like this. So when I entered the room, I saw the string like this. All the points are at the extreme. and you have taken x is equal to 0 at the node. This is the extreme position. So when you enter the room, if you see the string like this, and if this is the origin, then the equation will be 2a sine kx cos omega t. Let me take one more example. Let's say I write y is equal to 2a cos kx sine omega t. I'll reverse it. Now look at this. Amplitude 2a cos kx. If you put x is equal to 0, it's an antinode. That means you have chosen antinode as an origin. And at t is 0, y is 0. All particles are at mean. That means when you enter the room, you saw the string flat. It's moving, but at that instant it looks flat. And someone has chosen x is equal to 0 at the center, the origin. So the node will be x is equal to minus lambda by 4. This will be x is equal to lambda by 4 because the total length has to be lambda by 2. And the t is equal to 0. So for this position, the equation will look like this. Now, are you getting it? What does it mean? So be careful. So if you see something like 2a sine kx sine omega t, don't think it is not a stationary wave. It is still a stationary wave. It all depends on where you're looking at. So what do you think this will look like? Y is equal to 2a sine kx sine omega t. And y is equal to 2a cos kx cos omega t. Try. I'll give 30 seconds. How do you think they should look like? Let's see. So sine kx, if you put x 0, you are getting 0. So in sine omega t, so string is flat. So that second part of the equation, right? This is SHM, everyone. See, this is SHM. What is sine omega t? Particles at mean position. What is cos omega t? Particles at extreme position. And sine kx, so you are choosing x is equal to 0 at node, and the string is flat. Cos omega t, string is at extreme, and you have taken antinode as origin. All clear with this? So I can have any combination of sine and cos. So it's not like only that sine kx cos omega t is the thing. Clear with this? So let me give you one more. You try to draw for that. Now you won't be so lucky to get something so neat every time. What if I give you y is equal to 2a sine kx plus pi by 3 sine omega t plus 7 pi by 4. Fundamental frequency, yeah? Matlab one loop. Draw the shape. Draw the string at t is equal to 0. Let's see. Now, again, the first kx plus pi by 3 will tell you the position of the node. So you just need to find the position of the node. Start from there. So what is the amplitude? So listen carefully once. I'll show you one. So amplitude is 2a sine kx plus pi by 3. So for node, amplitude is 0. So simply write kx plus pi by 3 is equal to 0. So this is 2 pi by lambda, x is equal to minus pi by 3. X is equal to minus lambda by 6. So what is 1? Second thing, look at the second part. Like I said, this is SHM. What is 7 pi by 4? That is a by root 2. Now see, this is x is equal to 0. This is x is equal to a. This is x is equal to minus a. So 7 pi by 4 meaning if I add 45, you will complete a circle, right? Means you're 45 degrees short of completing a circle. Meaning this guy has gone up and came down and then it is going up. And it is at x is equal to minus a by root 2 going towards the mean. Does that make sense? We have done this kind of things in SHM. There, now you know how the thing looks like. So if your string, this is your mean position, this is your extreme position, your string is in the lower half of the loop. And where is the origin? Origin is somewhere, but look at this position here. This is the position of the node. Matlab your node is here, x is equal to minus lambda by 6. Your origin is somewhere here, x is equal to 0. Your antinode is somewhere here. And this guy is x is equal to lambda by 3. Because the total distance has to be lambda by 2. So the meaning of this is from the origin, lambda by 6 ka piche, there is a node, isn't it? Is that making sense? So that is the first thing. And where is the string here? String is at a by root 2. That means all the points are at 1 by root 2 of their displacement. That means your anti-node is at 1 by root 2, 2a. Isn't it? Anti-node ka displacement is 2a, 1 by root 2 times. So this was the position of the string, and this is going towards mean. So someone has looked at the string like this, and that is the equation he got. Is this making sense, everyone? Let me give you one more like this. But any doubts on this? So the second part is your SHM. The first part, just put equal to 0. You will get the position of the node. That's it. There is only two parts to that. Suppose if I give y is equal to 2a sine kx plus 2 pi by 3 sine omega t plus 2 pi by 3. Now draw. Let's see. So at node, amplitude is 0. And 2 pi by 3 meaning where is the particle? 2 pi by 3 is 120 degrees. You're 60 degrees short of reaching the mean again. So that is root 3a by 2, right? 60 degrees means root 3a by 2. So this guy has gone up and he's somewhere here. X is equal to plus root 3a by 2. And coming towards the mean. That is your mean position. That is your extreme position. So your string is something like this. So this guy is at a distance of root 3 by 2, 2a, which is root 3a. This is going towards mean. And you're saying the node is at a distance of minus 2 lambda minus lambda by 3. So actually origin is somewhere here. And this is x is equal to lambda by 6. Clear with this? Antinode is somewhere here. That's another lambda by, you can calculate that. Lambda by 3 minus lambda by 4. Lambda by 12. Clear with this? So generally to keep our life easy, we keep that origin at antinode or node. And we generally try to observe the string when it is at extreme or mean. Then you will get that phi 1, phi 2 will not be there. Then it looks neatly sine, cos, sine functions. But if they decided to mess up something like this is how the questions will be framed. Now let's combine everything that you learned in stationary waves and see how they can ask a paragraph question. I think if you get this question, then you understood stationary waves on a string. So we have a free end. This is 2 kg. Mu is 2 gram per meter. This is oscillating in second overtone. This is x is equal to minus 1 by 4 meter. This is x is equal to 9 by 4 meters. Velocity of the particle maximum, basically that's your antinode, is 10 centimeter per second. At t0, all particles are at half of the maximum amplitude. So now I'm giving you the picture, I'm giving you the data and asking the equation. Half of the amplitude and going towards mean. Find the equation of the wave. Find the equation of the stationary wave. It looks scary, but if you actually understand what happens with a free end and you know there is a general equation, then it starts making sense. So if you have no idea about the general equation and this thing, this will look like weird, like what the hell are those coordinates? So indirectly, what am I asking you to find? So see, this is your general equation. Y is equal to 2a sine kx plus phi 1 sine omega t plus phi 2. So you need to find 2a, you need to find k, phi 1, omega, phi 2. If you can find these 5 values, my job's done. Get them. You got 3-4 minutes. any answers? I think first of all, see, it's a free end. So how does a second overtone look like? Remember, even harmonics are missing. So second overtone is a fifth harmonic. The picture will look like this, isn't it? 5 half loops or 2.5 loops. This is the first thing. Second overtone is fifth harmonic for a free end. So from there, I can find the wavelength. And if I can find the wavelength, I know mass is given, mu is given. From here, I can find the wave speed. If I can find the wave speed, I can find omega. If I can find omega, then amplitude Vmax is 2a omega. I can find amplitude. There you will get k omega a aa jayega directly. Try. I'll give you a minute now. And getting 5152 is a game. Let's see. This is how it looks. Second overtone or fifth harmonic. They should know how free end ka sonometers work. So if you have no idea, then you're gone. This is x is equal to minus 1/4, and that's 9/4. So length is 2.5 meters. So there, lambda is 1 meter. So k will be, yeah, this is 5 lambda by 4. So lambda will be 2 meters. K will be 2 pi by lambda. K ka value is pi. V wave is root over T by mu. So here, be careful. Tension is 20 Newton because it is a 2 kg mass. And what is mu? Mu is 2 into 10 power minus 3 kg per meter SI units. Don't put 2 there. That's a mistake. Some people do. So this comes out to be 100 meter per second. If you put 2 there, you'll get root 10. You goofed up. Then if you know V wave, then that will be omega by K. Yeah, say omega aa jayega 100 pi. And we know Vp max will be amplitude of the particle. In this case, antinodic amplitude is 2a into omega is 0.1 meter per second. So 2a will be 1 by 1000 pi. Small amplitude makes sense. And we also know your amplitude is 2a sine kx plus phi 1. And you're saying your node is at x is equal to minus 1/4. So just substitute there. So minus k by 4 plus phi 1 must be 0. So phi 1 is 45. 5/4. Phi 1 bhi aa gaya. Now phi 2, there is a problem. Look at the word. All particles are at half of the amplitude and moving towards the mean. Now, when you say that, it's actually kind of vague because what you are asking, there are two possibilities. One possibility, you're at x is equal to a by 2 and you're coming down like this, means you went up and you're coming like this. So this will give you a phase angle 5 pi by 6, 150 degrees. Second thing, you can be below x is equal to minus a by 2 and you're going up. This is also a possibility. Since we didn't tell you whether it is positive or negative extreme, no, there are two possibilities. This must have traveled all the way like this. That means you're 30 degrees short of the phase angle. So this is 11 pi by 6. So for phi 2, there are two possible answers. Since it's not clear exactly what you're asking. Clear with this? There, you got everything. Have a look at this. This is how they'll put a question in a paragraph or a matrix matching. And if they decide to make your life more horrible, then they'll put a thin string and they'll put a thick string with a ring. I can add a composite string. There, they still know how to do. So thing is, how to do each individual part. There, that is about stationary waves on a string. So with that, we have completed waves on a string. So if you're doing HCV, there are two different chapters, waves on a string and sound waves. You can start doing it, right? Don't wait for the chapter to get over because it's a sound waves will get over fast. It'll take another maybe 2 to 3 classes max. It's a small one compared to this. You will see all exactly similar things. We have Doppler, which is removed from mains portion, but advanced May last year tha. This year they might change, we don't know, but we'll still do it just in case. Right. And after that, wave optics will take another 3.5 classes. So we will do that. But start doing waves on a string. So then we'll start off with the sound waves after the break. So take a break, come back by 9:37. We'll continue after this. Any doubt so far? Chalo, come back in 5 minutes. So next thing, sound waves. Again, end of the day, if you remember how we defined waves, it's simply a propagation of disturbance. So when we studied waves on a string, what we studied was the displacement of the particles was the property that we studied. So when sound propagates in a region, so what is the property that changes? So it's not actually a single thing, multiple properties change. Change in pressure, displacement of the particles. So when sound moves, the displacement changes, the pressure changes, density also changes. So there are multiple quantities that change. So you can study sound waves in any terms of this. You can even study this in terms of density. We prefer to study in terms of pressure because we are, we are more sensitive to pressure. If you see how your eardrum works, so if this is your eardrum, pressure inside is P naught, outside is P naught. So when a compression comes and hits your eardrum, P naught plus delta P, your eardrum actually stretches inside. When a rarefaction hits P naught minus delta P, your eardrum actually comes outside. The eardrum is continuously oscillating in and out. And you have your nerve cells here, which are getting activated because of this vibration. And that is how your brain knows that there is a, sound transmitting. So when you say, what is the difference between frequency and intensity? What do you mean by a sound of high frequency, high intensity? Physically, if you try to see, think of like this. A high frequency meaning simply you're sending more waves per second. See, for example, like this. If I'm making sound like, like tuck, 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 and if I make sound like tuck, 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 you can see both the sound. One is a high frequency sound, one is a low frequency sound. What do you mean by high intensity? If I say high intensity, low intensity, meaning I'm putting more energy, I'm putting less energy. So you can have a sound which is high frequency, high intensity. You can have a sound low frequency, low intensity, or any of these combinations. So when you have a high intensity sound, what happens? Your eardrum stretches a lot. So if you're hearing loud, loud sounds, your eardrum can tear. You become deaf. High frequency sounds, on the other hand, they don't damage much, but they irritate you. They oscillate so fast, your nerve cells get irritated. So this is the thing which you hear, when someone scratches a board, or in your class, you must have sometimes pulled a bench and the bench must have made a very key sound. These are all high pitch sounds, basically. You can even get an app, on your phone. You can get an app called Frequency Generator. It's a free cost. You can download that and see you can generate frequencies from 0 to 20,000. Our range is 20 to 20,000. I think around 5,000, 7,000 hertz ka frequency, you start getting irritated. So your ears will start ringing. It feels very weird. It doesn't pain, but it irritates. So once you exceed around 18, 19,000, you can't hear, but dogs can still hear. So if you have your neighbor ka dog and you want to harass it, so you can do something like that. You can put a high frequency sound. Just make sure that thing doesn't get pissed off. It jumps on you and bites you right and left. No, that's a different thing. You have to be careful because that can hear and you can't hear. So you kind of save, but the dog gets irritated. So, so you can actually use all these things, to make non-lethal weapons. Let's say if there's a big crowd and you want to disperse them and you can hit them with high frequency waves, people, nothing happens to them, but their eardrums can rupture or you can irritate them. Right. So something of that sort. So we prefer to study in terms of change in pressure. Again, see the word, I'm not saying pressure, I'm saying change in pressure. We will talk about that. That was a CET question. In sound, we study what? Pressure and change in pressure. The answer was change in pressure. Since humans and instruments detect pressure, yeah, you can make them see other things, but pressure is the most easiest one. That means now your general equation, which we wrote for waves, remember this y is not the displacement, this y is the displacement change in property. So this is your progressive wave, y is equal to kx plus or minus omega t plus phi. Y is the property. So our equation becomes like this now. Delta P is equal to delta P max sine kx plus or minus omega t plus phi. So this is your change in pressure. This is called pressure amplitude. There. Now, henceforth, when we say amplitude, we will always mention whether it is displacement amplitude or pressure amplitude. Because in waves in a string, we didn't have a problem, but here we have a problem. Because we can study sound waves both in displacement and pressure, we have to tell every time. Are you talking about displacement amplitude or pressure amplitude? Clear with this? Now, if there is no sound in a region, the molecules will be equally spaced. And the pressure area will be P naught, which is 10 power 5 pascals. But when sound travels through a region, you'll find there are certain regions with compressions and certain regions expand. So here the pressure becomes P naught plus delta P max. This is your compression. And here it is P naught minus delta P max. Rare fraction. So this delta P is around 20 to 30 pascals. It's not a huge change. Meaning, normally think about it. The normal pressure you are there is 10 power 5, and your ears can detect a change of 20 to 30 pascals. If you see in terms of percentage wise, it's minimal actually. And here delta P can be positive or negative. This is the catch. If you try to study pressure now, you can't have negative pressure. So delta P can be positive or negative. So the pressure is fluctuating between 10 power 5 plus or minus 20. So 20 degrees. So you're taking 10 power 5 as mean, and about that it is oscillating. So delta P can be positive or negative, but pressure is always positive. You can't have negative pressure. Clear with this? So about 10 power 5 as a mean position, the delta P is oscillating. So when you say rarefaction, it doesn't mean a negative pressure. It's 20-30 pascals, not less than the regular pressure. When it's a compression, same thing, 20-30 pascals more than the regular pressure. Clear with this? No. Great. So we know the particles are moving and we know it's also getting compressed. So what is the relation between them? Now again, the derivation is not really that important, but let's see. The result which you get is more important. Consider a region with bulk modulus B. I hope you remember bulk modulus is nothing but minus dP, change in pressure by dV by V, volume stress by volume strain. So take a small region where x coordinate is x and this x coordinate is x plus dx. So when the wave is traveling, let this particle at x travel by distance y, the particle at x plus dx travel by distance y plus dy. And let the area of cross section be S. So here we get the change in volume. So volume V will be area into dx because that region ka length is x. Change in volume delta V will be S into dy. Look at this. If this goes y and this also goes y, there's no change, isn't it? But if one goes y and other goes y plus dy, then the volume is changed by dy ka length, so S into dy. Now apply this in the bulk modulus ka formula. We get minus dP dV by V. So we get dP is equal to minus bulk modulus dou y by dou x. There, that's your formula, everyone. This is the relation between pressure and the y, which is the displacement of the particles. So change in pressure at a point is minus bulk modulus into dou y by dou x, where y is the displacement of the particles from the mean position and x is the x coordinate of that particular point. Remember, even in a longitudinal wave, the particles are still oscillating in SHM, but they're oscillating in and out of the same wave of the wave. Clear with this? So let's see what happens if we apply this to our regular equation. So dP is minus bulk modulus dou y by dou x. So this is the relation between displacement and change in pressure. So whenever a sound wave travels in a region, it pushes the particles front and back. At the same time, the waves get compressed and expand. So both are happening at the same time. These are not two independent events, both are related. So if you take your regular equation, y is equal to a sine kx minus omega t. This y is your displacement of particles at x coordinate. Dou y by dou x will be ak. cos kx minus omega t. Then your equation becomes dp is equal to minus bak cos kx minus omega t. But we prefer to write in terms of sine. So you'll get dp is equal to bak sine 90 minus theta. So minus goes inside. So minus 90. You can also write that as 270 degrees. So now if you look at the equation here, this BAK term is actually your delta P max. This is the relation between your normal amplitude and the pressure amplitude. So you'll notice few things here. So delta P max is bulk modulus, amplitude K. So that means whenever a sound wave travels in a region and if the particles oscillate with an amplitude A, they create a pressure which is BAK. A is your displacement amplitude. That means higher the bulk modulus, more pressure you get. K is to power lambda. So lower wavelengths create more pressure. Second thing, if you observe, if this phase angle is 0, this phase angle is minus 90. So displacement and change in pressure are out of phase by 90 degrees. This will be a theoretical question. That means whenever the displacement is maximum, then dp is at mean position. When displacement is at mean position, pressure is at extreme position. Basically, one is sine and one is cos function. So this statement now I misunderstood. So when one is mean, other is maximum. So that is what I remembered. 2010, I guess. I passed out from IIT and I gave an interview somewhere. They asked a question. I goofed up big time. Let me ask you the same question. Clear with this? So these are the main formulas in this. Delta P max is BAK, dP is equal to minus bulk modulus dou by dou x. And the phase angle is 90 degrees. Let's see a question. So the question they asked me was this. It's a YX graph for a longitudinal wave. Be careful. So this is not the y is the not the displacement of the particles up and down. A regular sine wave. That means if this is x, the particles are oscillating to and fro. So this is y. There were 4 points A, B, C, D. The question was which points have maximum pressure and minimum pressure? If I ask you the second question, it becomes more clear what I'm asking. But when I was there, so they asked me this much only. I thought something else. I told something else. It was wrong either way. So second question, which points have maximum change in pressure? I gave them big answer. You guys try. One, we can do this pure mathematically. I'll also show you a way to visualize this. Let's see. Some of you got it, some of you did the mistake. I did. Okay, let's see. Let's see first of all mathematically, because if you do it mathematically, there is no doubt. There's nothing to think. You've thrown all your, what do you call it, feelings and logic out of the thing, and you're just getting answer mathematically. So what is your dP? Minus bulk modulus dou y by dou x. This is nothing but your slope. So here the slope is positive. Here slope is 0. Here slope is negative. Here slope is 0. That means at B and D, there's no change in pressure. dP is 0. So therefore, pressure at B, pressure at D is equal to P naught. If you look at A, slope is positive, but it is minus. So pressure at A is P minus delta P max. That is the maximum slope there. This is your minimum value. Pressure at C is P naught plus delta P max. This is the maximum value. B and D are nothing. And who has the maximum change in pressure? A and C have the maximum change in pressure. So that is a catch. A and C have maximum change in pressure, but one change is positive change and one change is negative change. You getting the problem? So when you read that statement, right, when it is phase of out of phase by 90 degrees, people think like, "Arey 90 matlab maximum minimum ho jayega." No, one is a positive maximum, one is a negative maximum. So the question, right, if the question had been this, where do you get the maximum change in pressure is different. Maximum pressure, minimum pressure is different. So A and C have maximum change in pressure. Clear, everyone? Now, how to think about this intuitively? Now, when you want to do this, forget about the points exactly. Don't look at point A, look at the point before and after A. Observe particles before and after A. So let's say I take three particles, one behind A, one at A, and one at before A. So now look at this thing. The particle at A has zero displacement, so that will be there only. The particle in front of you has positive displacement, mean that particle has gone ahead. This particle behind you has negative displacement. That means this particle has gone back. So what is happening here? That region is expanding, right? If the particles are going away from you, this region is expanding. Means it's a low pressure region. It's a rare fraction. Similarly, look at C. If you look at a particle in front and the particle behind, the particle in front of you has a negative y, means it is coming back. Particle behind you is going front. So this is getting compressed. So C ka pressure is maximum. Making sense? Then what is happening at B? At B, this is what is happening. If you take particle in front and behind, this particle is going front, this particle also going front, this particle also going front. Did the distance change between them? It neither compressed nor elongated. The region ka volume is same. That's why the pressure didn't change. Clear with that? This is more intuitive way of figuring it out. So in case you forgot that formula, you can always use this. Clear with this? But that mathematical thing is clear. Matlab, there is no doubt about it. You'll get the answer properly. Understand what you get is dp. I never said that's not the maximum pressure. dp can be positive or negative. Clear with this? Let's see one more. Let's say speed of a sound wave is 330 meters per second. The frequency is 165 hertz. Amplitude is 2 into 10 power minus 6 meters. The difference between maximum and minimum pressure is 20 pascals. Find bulk modulus. Yeah, this is just formula based. It's an easy question, formula based, but there's a small trap. Let's see whether you figured it out. What is the formula we have to use? Delta Pmax is BAK. That's the formula we just now derived. You should remember that. Quite an important result. That is the only formula which will give you the bulk modulus from there. So great. V wave is omega by k. Omega is 2 pi f by k. So k will be 2 pi, f is 165 by 330. This will be pi. Look at that statement. That statement is actually messed up. The difference between maximum and minimum pressure is 20 pascals. Most people will write delta Pmax as 20. No, I didn't say that. The difference between maximum pressure is P naught plus delta Pmax minus the minimum pressure in the region is P naught minus delta Pmax is 20 pascals. I would have said like this then. The maximum change in pressure is 20 pascals. So be careful. Change in pressure and pressure are two different things. So what you actually got, 2 delta Pmax is 20. So delta Pmax is equal to 10. So if you don't do that, you'll get an answer of 2 made difference and the whole thing is gone. And then you're done. This is B. A ka value is 2 into 10 power minus 6 and K ka value is pi. Therefore, bulk modulus will be 10 power 7 by 2 pi. Easy. Just start to be careful with the formulas. Next thing, speed of a longitudinal wave. Again, we'll not get into the derivation for the speed part. So remember, we're writing for longitudinal wave, and that sound wave is a special case. So when you say longitudinal wave, it can be waves in a fluid, sound waves, is given by root over bulk modulus by rho. Same thing, if you take longitudinal wave in thin rods, now for thin rods, there is no volume defined. So we define Young's modulus. Rho is your volume density. Yeah, you should definitely remember these formulas. So how do these things work? All clear so far? Yeah, there's a bit of a theory. Let's say we have a rod. You take a hammer and you beat it this way. You hit it perpendicular to it. Then you'll notice the rod, right, actually get a bump like this. So you can clearly see particles are going up and down. The bump is going up and down, but the wave is traveling forward. Sorry. This is your transverse wave. Now, if you approximate this to be like a string, you can write this to be root over T by mu. The same rod. If you take the hammer and hit it like this, then you will see a bump. And this bump is oscillating front and back, and the wave is going this way. This is your longitudinal wave. So you can actually generate both the waves in a rod. And this is what actually happens during an earthquake. In an earthquake, we get something called P waves and S waves. P waves are pressure waves, and S waves are shearing waves, which are actually transverse waves. So whenever there's an earthquake, you actually get hit by two different waves. So we will see the speed which comes first of all, which comes faster. So if you try to find the ratio of V transverse by V longitudinal, this is root over T by mu by rho by Young's modulus. We know Young's modulus is equal to tension length by A into delta L. So T by Y is A delta L by L. And rho is equal to mu into area. So rho by mu is equal to area. Mu by area. So if you substitute all this, you end up with root over delta L by L. So V transverse by V longitudinal is given by root over strain. And we know generally strain is always less than 1. The body can't elongate more than its own length normally. Right? So that means V transverse is slower than longitudinal waves. So whenever the earthquake generates, the longitudinal waves will reach the surface first, and then comes the transverse waves. That means, so when an earthquake comes, first the waves will come like this. So the buildings oscillate up and down. Then comes your transverse waves. Then the building oscillates left and right. In which case you think the building will fall down. Think like this. If I put you on a floor and the floor is going up and down, will you fall down then? Or if I put you on a hanging bridge and if I make the bridge go left and right, which is more unstable? The left and right. So the second waves which come now, the shearing waves, that will collapse the buildings. Those are the deadly ones. So, but again, there's a very small gap between them. So what scientists do, right? Both the waves reach the surface at different times. By calculating the times between them, you can figure out at what point the earthquake has started. It's called epicenter. You must have seen this, the earthquake of 5.6 magnitude has occurred, and it occurred at a depth of 50 kilometers below the Earth's surface. Next time when you see the news, na suno wo statement aayega ek. They'll give you the position of the epicenter where the earthquake started. And this is also the whole, what you call, this is the only way we can actually study the earthquake crust. You must have seen, how do you know there's a core or mantle? Who dug 2000 kilometers hole and studied it? So what you do is actually you send these two different kind of waves, and then when they get reflected by some materials and come back, you actually see the difference in speeds. And from there, you try to figure out the density and all that stuff. And this is the technique also that you use to find mineral deposits and oil deposits. Right? So how do you know when you're testing that you're actually studying aluminum deposit or iron deposit or gold deposits? Because if that material has more iron content, then the speed of sound ratio will be different. The bulk modulus of iron, bulk modulus of aluminum will be different. So they'll have different time intervals. So scientists will study all that things. There will be a lot of calculations, and that is the reason, these things will give an estimate, but they're not always accurate. End of the day, you still have to dig a mine and then actually check whether it works or not. So anyway, that's one part of it. Then we want to find the speed of sound. The first person to give you something about speed of sound is, as usual, our Newton. No job, nothing. Just sits there and starts making everything. This guy is literally there everywhere. So we have Newton's speed of sound. Sometimes I feel like this guy might be a time traveler or an alien, or must be a fraud, like, who hired some 50, 60 scientists and he took all the papers on his name. Or he must be like, yeah, once in a lifetime genius. But again, if you see Newton also, right, whatever work he did is all in his prime. Once he crossed 30, this guy became so disillusioned with his, other things. Like he started working on alchemy. His final research and work was, in the last part of his life, he was spending a lot of time on converting lead into gold. He was trying to find something called a philosopher's stone through which you can convert lead into gold. That's all alchemy, actually. So when he died and when his papers were, sold off in an auction, when people brought it thinking there'll be some groundbreaking philosophies and all, they found alchemy and people were quite disappointed. But if you think about the scientists also, this is one common phenomenon actually. Most of these groundbreaking theories, right, come when they're young, and I think after 30, 35, things just die down. Same thing with Einstein also. But anyway, so Newton did groundbreaking stuff. How many places he is there? Newton's laws of motion, Newton's universal law of gravitation, Newton's law of cooling, Newton's law of viscosity, right? Newton's corpuscular theory and ray optics, Newton's speed of sound. In calculus तो है ही उसका बहुत. So there, I think chemistry छोड़ दिया. During that time, there was no chemistry, na. Chemistry came in after 1900. That's why he left it. So since sound propagates, I think maybe that's what happens, when people don't have access to internet. People sit and start figuring out a lot of stuff. Maybe we should try with that, all of you also. Take all of you, put all of you on some place where no internet, no telephone, nothing. Every day morning you'll wake up, make you run 10 kilometers, then put you in a farm, make you work in the farm, grow your own vegetables and food till 10 o'clock. And then 11 o'clock to 2 o'clock classes, then 2 o'clock food, then 3 o'clock to 5 o'clock classes, then again evening 5 to 7 farming, and then 8 o'clock some games, and 9 o'clock to you sit to study, and then 10 o'clock you're sleeping and waking up at morning 4 o'clock. Every Sunday we take all you to jungle, give you sticks and spears and hunt animals. Something of that sort. Who knows? You might all create some groundbreaking theories then. हो सकता है. No, anyway, so this guy, he started thinking, since sound propagates in atmosphere, and in atmosphere temperature is constant. Remember when I said when sound propagates, there is a compression and rate fraction, so gas is compressing and expanding. That means pressure, volume, and temperatures are changing. But he made a, it looks like a decent assumption. Since the sound is traveling in atmosphere and temperature of the atmosphere is constant, he assumed the propagation of sound is a isothermal process. That means PV is equal to constant. We have done this in elasticity, if you remember. So how do you get the bulk modulus differentiate on both sides? PdV plus VdP is equal to 0. So from here, we get bulk modulus is equal to minus dP. dV by V is equal to P. Then we use our formula root over bulk modulus by rho. So V sound will be root over P by rho. And we know from ideal gas equation, PV is equal to nRT. PV is equal to mass by molecular weight. Mass by volume becomes density. So you get P by rho is equal to RT by molecular weight. So this formula becomes root over RT by molecular weight. And when you calculated this value, this thing comes to around 280 meters per second. But unfortunately, in the experiment, we figured out the value comes out to be actually 330 meters per second. That's actually a pretty huge error. 50 out of 280, that comes to almost 20% error. So somewhere Newton's assumption went wrong, even though it looked logical. Then came Laplace. So it's called Laplace correction. So this is the main formula we will use. Laplace says, when the sound propagates through an air, the air compresses and expands so fast. Think about it. When you say 100 hertz, you're compressing and expanding the gas 100 times per second. Since the gas expands and compresses so rapidly, there is no time for heat exchange. And if there's no heat exchange, what process is that? Adiabatic. See, this is what you do in science, right? You make all assumptions, then you check with your theory. It works, great. Doesn't work, then you keep changing your theory. There's nothing absolute in science. If you ask me, the only subject that is absolute is maths. 1 plus 1 is 2. Even a dog knows that. How does a dog know? Imagine there is a room and there are 3 puppies. And it started raining there. The dog goes, takes the puppy, puts it back, goes, puts it back, goes, puts it back. It doesn't go the 4th time. It knows it. There's no need to go the 4th time. Dog does not know what is 1, 2, 3, but it knows the concept of 3. The dog knows I have 3 babies. Even that does not understand what is 1 and 2 and 3. So even animals understand intuitively. You can't teach them calculus, but yeah, basic maths, so they'll know. So since gas compresses, and expands rapidly, there's no time for heat exchange. So it's an adiabatic process. So then we can write PV power gamma is equal to constant. Differentiate on both sides. dPV power gamma P gamma V power gamma minus 1 dV is equal to 0. Bulk modulus is minus dP by dV by V is equal to gamma P. Now when you substitute that in the formula, root over gamma P by rho, and P by rho is nothing but RT by M. We get gamma RT by molecular weight. This comes to around 330 meters per second, which matches with the experiment. So remember, this is the speed of sound in gases. You can't use this in liquids and solids. Liquid and solids use bulk modulus by rho. Root over gamma RT by, this is the molecular weight in kgs. Be careful with that units. This is the correct formula. And I hope everyone remembers what is gamma. Gamma is Cp by Cv, adiabatic constant, which is 1 plus 2 by F. F is the degrees of freedom. Clear with this? Now, every time you won't be so lucky, they'll just give you a single gas. What if you have a sound in a mixture of gases? Then your formula becomes V sound will be root over gamma mixture RT by molecular weight mixture. Remember, temperature must be in Kelvin. And how do you get gamma mixture? 1 plus 2 by F average. And how do you get F average? N1, F1 plus N2, F2 by N1 plus N2. We have done this in thermo. Be careful, don't write like this. Gamma average will be N1 gamma 1 plus N2 gamma 2 by N1 plus N2. This is wrong. Gamma is not a linear function, it doesn't work. Similarly, molecular weight average will be N1 M1 plus N2 M2 by N1 by N2. So example, we have 2 moles of helium and 1 mole of hydrogen at 500 Kelvin. Then F average will be 2. Helium is monatomic, hydrogen H2 is diatomic by 2 plus 3. Helium ka mass is 4 and hydrogen ka mass is 2. 10 by 3. Substitute there, you'll get the answers. Again, remember this is 10 by 3 minus 3 kg per mole. So if they give you a mixture of gases, you use the gamma average and molecular weight average. Clear? Next thing, this is one important JEE question. Huh? If the pressure of the gas becomes 4 times, what will happen to the speed of sound? So if you remember the formula, V is equal to root over gamma P by rho. You can also write it as gamma RT by M. So there is a question like that. If the pressure of the gas becomes 4 times, what happens to the speed of sound? The thing is, nothing happens because P by rho is RT by M. What most people don't realize is when you increase the pressure, volume decreases, so density also increases. So P by rho ka ratio remains same. So speed of sound is independent of pressure. It depends only on temperature. If P increases, then volume decreases and rho increases at a given temperature. So the ratio P by rho remains constant. So be careful with that. Don't say it will double. Speed of sound is independent of pressure. Depends only on the temperature. again for a given gas. Third point, what happens if you increase humidity? So again, what is humidity? You're replacing air molecules with water molecules. What is the molecular weight of air molecules? Mostly nitrogen, 28. What is the molecular weight of water molecules? 18. You're replacing heavier molecules with lighter molecules. Speed of sound increases. Think of like this: in an extreme case, you put so much water, air becomes water. Sound travels faster in liquids. We are replacing air molecules whose molecular weight is 28. Water molecules M is 18. Therefore, speed of sound increases. That means on a foggy night, sound travels faster. Clear with this? So these are the 3 points there. That's a little about the speed of sound. So next class, when we catch up, we'll continue from here. And one more thing, next week, right? Monday, we'll be having a class as usual. But after that, we are